I'm Mikkel Peters, and this is Lab 5, Slinky. The purpose of this lab was to observe how drag and gravity impacted the freefall of a stretched Slinky. A computational model was constructed to compare the experimental data to the observed data. It was predicted that by incorporating drag and gravity, an accurate computational model would be produced that would match what was observed. This lab focused on the idea that the momentum principle, drag and tension, and spring force. And as a preview of the result, the computational data did not match the experimental data due to problems with capturing oscillations and preserved energy. Here's the theory behind this lab, starting with the momentum principle, which relates a force to the change in momentum over the change in time. We use this principle to derive the velocity and position update formulas, which allow us to use initial conditions such as force, initial velocity, mass, and change in time, in order to calculate final velocity and position respectively. Drag force is given by the magnitude of velocity squared times the unit vector v hat times the proportionality constant of drag, b. This will let us know how much air resistance is impacting the path of the Slinky. Tension is the force that acts opposite to a taut string, or in this case a Slinky, and in this case we are also using spring force, which is given by negative spring stiffness times compression or stretch of a string times the unit vector L hat, which is the direction that the spring force is acting in. For this experimental model, tracker was used to track the center of mass throughout the video. The system for this experiment was the Slinky, and the surroundings were the earth, air, person's hand, and everything else. Initial velocity was 0 as we started from rest, and we started 0.457 meters off the ground. In this example, tension was equal to the spring force of the fully extended spring, and it was observed that the bottom of the Slinky hovered while the top part pulled down, and that was from the tension in the Slinky, seen here. The data from this experiment was used to create a graph that will be shown in the results section. Here's the computational model constructed to predict the Slinky's motion. The first square establishes initial conditions, such as 0 velocity, height from the tracker model, and a mass of about 0.25 kilograms. The average weight of a mental Slinky. The trial and error 0.004 worked best as the drag proportionality constant. This second section here covers the first phase, where the Slinky kind of hovers in place as gravity pulls the Slinky downwards, but the tension from the top half of the spring is pulling upwards, creating that hovering. This is followed by updating the position and velocity in the code. This third section covers the phase of the free fall after the Slinky is compressed and tension dissipates and gravity is just pulling downwards. Here we incorporate drag to model any air resistance that the Slinky might face while flying through the air. Here we see that there is in fact a plateau, and this is equivalent to that portion where the bottom of the Slinky is hovering. And then we see that there is a gradual change downwards as gravity is able to act on the Slinky. When we compare the experimental model to the computational model, we do observe that both models plateau to at the same point, and both have a drop-off. However, we see here that we have these really big drops in position that aren't seen in the computational model. From this, we can conclude that there might be another force acting on the Slinky. Possible sources of error include errors in the manual tracking, such as not being in the center of mass, or in the coding process, there could have been errors. For our what-if question, we ask, what if the computational model accounted for conserved energy from the first portion of the Slinky's movement? Since there is probably residual movement from the oscillations and reserved energy from when the Slinky was still pulling up on the bottom half of the spring, there would most likely be an increase in the velocity of the graph seen in the observational model, and we would have these more sharp decreases in the position. And this would lead to an increased accuracy of the computer model, and it would probably more likely match the real-world scenario.